FlexVPN Smart Defaults. Let's begin. One of the challenges we're very likely to face in a real-world environment is that we have, for example, a hub router, which is a lot of power and features, and we have a branch router, which maybe doesn't have quite so much. And regarding an IKE version 2 proposal, R1 may support a larger set of NGEs, the next generation encryption protocols. For example, Diffie-Hellman Group 19 or 20, which both use elliptical curve cryptography, as well as 14, which is 2048, and maybe on the branch router, it just simply doesn't have the iOS and the feature set that supports all of those Diffie-Hellman groups. So this is the Diffie-Hellman right here, and that's one aspect of the proposal. As part of the proposal, it also specifies the hashing method for data integrity, and maybe the hub router supports SHA-512. It's also safe to say that if this router supports SHA-512, it'll also support SHA-384 and SHA-256 as part of its IKE version 2 proposals. And the major third piece in the proposal is the encryption. And if R1 supports AES 256, it'll also support AES 192 and AES 128. So here's the big three in the IKE version 2 proposals: the Diffie-Hellman group, the encryption we're going to use, and the hashing algorithm we're going to use. Now, fortunately for us, in the IKE version 2 proposal, it can offer multiple hashing methods and multiple encryption methods and multiple Diffie-Hellman groups. And the configuration of this proposal for IKE version 2 is a lot simpler than it is for the older IKE version 1 ISAKMP policies. And that's because with ISAKMP, if we had 3 different encryptions and 3 different Diffie-Hellman groups and 3 different hashing algorithms for data integrity, that'd be like 18 different ISAKMP policies if there was 3 each. So with a single IKE version 2 proposal, we can bundle all of those options into that proposal, and they can be used for the negotiation of the IKE version 2 with the peer. We can use the default proposal, which, depending on our platform and how many encryption sets we support, may vary a little bit. However, it's highly likely that at least one Diffie-Hellman group, one encryption algorithm, and one data integrity algorithm, or hashing algorithm, from the default proposal will be compatible with R2 if it's using its IKE version 2 default proposal with the hashing, encryption, and data integrity elements that it has in its default. Now, one of the cool things that we can do if we need to or want to is we can change what's in the default proposal. So we could either use the defaults, for example, the default proposal, or we could change that default proposal and still use it. And one of the benefits of using the default proposal, whether it's the native one that came with the system or one that we've tweaked, is that the IKE version 2 policy is already linked to the proposal called default. So by simply changing the default proposal, the name of it is still default, and it's still being called on by the default IKE version 2 policy, and that saves us a step. Because if you and I created a brand new IKE version 2 proposal, we'd also have to go visit the default policy and tell it specifically, oh, by the way, don't use the default proposal, go ahead and use the proposal that we just created. One other interesting note that I want to point out regarding IKE version 2, in a comparison over to IKE version 1, is that in IKE version 1, we had our haggle, where we were going to negotiate the hashing algorithm, the authentication, the Diffie-Hellman group, the lifetime, and the encryption. And I'd like to point out some subtle differences with IKE version 2 in that the hashing, the Diffie-Hellman group, and the encryption are all part of the proposal, which is this guy right there. And those are the 3 elements that we identified earlier: Diffie-Hellman group, encryption, and data integrity or hashing. However, if we take a close look at the proposal, it doesn't have the details regarding lifetime for the IKE version 2 tunnel, nor does it carry the details regarding how we are going to authenticate with a peer. Those 2 portions, the A and the L, the authentication and the lifetime, those are going to be found inside of the IKE version 2 profile. And in the profiles where we have our match statement, where we could match on the IP address of the peer, or match on the FQDN of the peer, or the email address of the peer. And in that profile with our match statement, that's where we're going to specify the authentication of how we're going to authenticate that peer, as well as the lifetime. So I would encourage you to write that out just as a little reminder regarding IKE phase 1 and how it used to be with the haggle and how they've broken it out specifically in IKE version 2, with the H, G, and E being in the proposal and the A and L being in the profile. Now the piece up here that we'd also need to add, of course, is the key ring if we're using pre-shared keys for authentication. And in the profile, we'd point to the correct key ring that holds that information for that authentication. Now there's also some smart defaults regarding IPsec, specifically for the transform set and the IPsec profile. And here's how these are linked together. The default profile, which we are going to apply, for example, to a tunnel interface, that default profile is going to call upon the default transform set. So if you and I wanted to, we could save the steps of creating a custom transform set if the default's okay. And we could also avoid having to create an IPsec profile, because we could use the default profile, which is calling on the default transform set. And if we needed to tweak any of these aspects, we could tweak the default transform set, and the default profile would still use it. And all of this is in the attempt to help reduce the amount of configuration that we have to do every time we deploy IKE version 2. So what you and I get to do is we're going to take these two routers. These are two different routers than the routers I used in the previous video. There is no IPsec configured on them whatsoever. They're running 15.3x. They both support IKE version 2. And what I've noticed is that as the versions of iOS get bigger and bigger, sometimes they make a slight modification for one or more commands, making it a little bit different than a previous version. And the reason I point that out is because if you get to a certain syntax you think should work, you need to make sure that number one, it has the feature set to support the feature you're trying to use. And secondly, if they've modified the command a little bit, use a question mark and see what the correct syntax is for the completion of that command, and you'll be able to push right through it. So what you and I get to do is we're going to take the default proposal and we're going to change it. We're going to take the default transform set and we're going to change it. And when the default policy for IKE version 2 looks for the default proposal, it'll be using the changes that we made there. And when the default IPsec profile looks for the default transform set, it'll see the changes we put there as well. It'll also be a great opportunity to review the commands that we'd use for implementing FlexVPN. To start off, let's just verify we have basic connectivity from R1 on the left over to R2 on the right by pinging to 25002. That looks great. For IKE version 2, let's take a look at our default proposal, which is the proposal called default with the command show crypto IKE v2 proposal default. So this IKE v2 proposal for encryption has three offerings: AES 256, 192, 128, so 3 there. For data integrity, aka hashing, it's got 1, 2, 3, 4, 5 there. And for the Diffie-Hellman group, it's got 2 options: Diffie-Hellman group 5 and Diffie-Hellman group 2 for 2 options. In IKE phase 1 of IKE version 1, if we wanted to have that many options with 3 times 5, which is 15 times 2 more, which is 30, we would need 30 IKE phase 1 ISAKMP policies to have that many combinations. The PRF stands for pseudo random function, and it's used by IKE version 2. And if it's not specified, it's just going to follow the same hashing methods that we have for the data integrity. We have our IKE version 2 default policy, which is wide open by default. We can see it with a show crypto IKE v2 policy. And it doesn't care about anything about VRFs. It's not restricting any IP addresses. And the most important part about this default policy is that it's calling upon the default proposal, which has these elements that can be negotiated as part of IKE version 2. We also have some really cool defaults for IPsec. If we do a show crypto IPsec transform dash set default, without any configuration, we have this default transform set that can be used. And a question I have for you is, do you remember where we would use a transform set? Well, in this case, we're going to go ahead and put it as part of an IPsec profile. And as luck would have it, the default IPsec profile, which there is one by the way, and it is calling upon that default transform set. A show crypto IPsec profile default will reveal that to us. So this default IPsec profile is using the default transform set right there. It's simply showing us the contents of that default transform set of AES and SHA. And the default IPsec profile is not using PFS. PFS says, okay, for the IPsec tunnels, we want our own set of keying material. And so if PFS is enabled, perfect forward secrecy says, let's run Diffie-Hellman again and generate new keying material that the IPsec assays can go ahead and use. And we have a default lifetime of 3,600 seconds for an IPsec tunnel that's built based on this default IPsec profile. Now the cool thing is we can change those defaults if we want to. An example of that would be, let's go into configuration mode. We'll say crypto IKE v2 proposal default, and let's change the encryption, let's change the integrity, and we'll change the Diffie-Hellman. And the reality is, anything we change here is also going to affect any other systems that are using the default IKE v2 proposal. So a moment ago, that IKE v2 default proposal had a whole bunch of different encryptions and hashing algorithms and Diffie-Hellman groups. Now, if we do a show crypto IKE v2 proposal default, it's a much different story. It has the encryption that we specified, it has the hashing that we specified, and it has the Diffie-Hellman group 2 that we specified, and that's it. So just be aware that if we're building a whole bunch of IPsec based on some defaults, if we change those defaults, it's going to affect those other tunnels that are using the defaults. I also want to share with you how we can set the defaults back. For example, if we wanted to have the Ike v2 proposal back to its default condition, we use the command default crypto Ike v2 proposal, and then poof, it's back to its default. We can verify that with a quick show crypto Ike v2 proposal default, and it's like magic. This little default command right here took our customized Ike v2 proposal and it basically wiped it out, and now we're back to the default Ike v2 proposal. So primarily for the purpose of demonstration, let's customize an Ike v2 proposal that we can actually use here between R1 and R2. And to do that, we're going to do crypto Ike v2 proposal default. And now anything we do here is messing with the default proposal. So let's change the encryption to say AES 256 and AES 192. For data integrity, we'll do SHA-512, 384, and 256. And let's specify 4 different Diffie-Hellman groups that we'll support. So during our negotiations, we're going to send all of this over as far as what we're willing to do. And the receiving side, as long as there's a compatible data integrity for hashing and encryption for confidentiality, and the Diffie-Hellman group that we're going to use to generate shared secret keying material, as long as the peers can agree on at least one of those from each category, they can get the ball rolling in their Ike version 2 conversation. I always like to verify what we configured, so let's do a show crypto Ike v2 proposal default just to confirm that what we put in is now showing up as the default. And that looks great. Next, let's create a keyring, and we'll call this keyring Ike v2 keyring our-keys. We'll set up our peer, which is R2. His address is 25002, and previously we did the identity based on an FQDN. Now let's do an identity based on the address, and we'll specify the pre-shared keys we're going to use for the authentication with R2. Now in this example, we're going to use the same key on both sides, but as we demonstrated in the previous video on FlexVPN, we could use different keys here. In this example, however, we're using the same pre-shared key for authentication of both sides. Next, let's create the Ike v2 profile, and just for fun, let's go ahead and call this default as well. And it states, okay, in this profile, you need to specify how you're going to authenticate. The keyring says what the passwords are, and in the profile, we'll specify the method. So if we want to use RSA signatures or if we want to use pre-shared keys, we need to specify it in this profile. And it's a lot like an if-then statement. So let's put our if clause in there. Match identity, remote, address 25002. Now in the previous video, we matched based on the FQDN. Here, we're going to match the identity based on the actual IP address. And we'll also configure R2 with a compatible policy so that when he sends his identity over, he'll be sending the IP address of 25002, and that way we can, quote unquote, identify him. Now when R1 communicates over with R2, it also needs to identify itself. And we want to specify that R1 should use the local identity of the IP address 15001. In this profile, we're also going to specify the authentication method that we should use with this peer. So we're going to say we're going to use local authentication with pre-shared key and remote authentication with pre-shared key. And of course, we need to refer back to that keyring to get the information about those keys to use for that authentication. So we'll tuck that in there as well. Keyring local our-keys as opposed to getting the keyring from, for example, a AAA server. And that is one of the differences, by the way. On the system I was using in our previous video, it didn't have this local keyword. It was a slightly older version. And on the newer version of iOS, with the Ike version 2 support, we have the ability to use a AAA server for the actual key information as opposed to using it locally. So our local keys are in this keyring right here called our keys. And just for grins, let's go ahead and specify that the Ike v2 lifetime in this profile is going to be 7,200 seconds. So as a reminder, in the proposal for Ike version 2, we have the hashing, which they call integrity, we have the encryption, and we have the Diffie-Hellman group. And it's here in the profile that we're specifying the authentication method. In this example, we're using pre-shared keys, as well as the lifetime. Now in the older Ike version 1 and phase 1 of Ike version 1, all of these items were negotiated as part of the ISAKMP policy. However, with Ike version 2, these 3 elements are part of the proposals for Ike version 2, and these 2 elements are part of this authentication profiles for Ike version 2. Now let's move on to IPsec. For IPsec, we do have some defaults. For example, if we do a show crypto IPsec transform-set, we'll have one default transform set because we haven't created any new ones yet. And if we want to use that, we can, or we can tweak that transform set. So in this example, I'm going to change it from using AES and SHA-HMAC, and we're going to specify that we want to use ESP-GCM, which is part of that next generation encryption protocols. And we also have a warning saying, hey, the default transform set's been modified. You just changed it to this. If you're using this default transform anywhere else, those other uses on this same router are going to be impacted by the changes that we just made. And we can verify the changes that we just made with a show crypto IPsec transform-set, and it should match exactly with the new information we just gave it. So previously, the default was using these transforms, and now it's using GCM 256 because we told it to. Now there's also a default IPsec profile, and the key element about the default IPsec profile is that it's using the default transform set by default. So we do a show crypto IPsec profile default. The default profile says, yep, I'm using the default transform set. We just modified it to be ESP GCM 256, and so it's reflecting that here. PFS, perfect forward secrecy, is not being used by default. And here we have the default lifetime that's going to be applied for any tunnels, IPsec tunnels, that are generated due to this IPsec profile being applied to a tunnel interface. However, if we want to change it, we certainly can. We can go ahead and type in crypto IPsec profile default, and then say, let's set the PFS to group 20. That's a good one. It uses that really cool elliptical curve cryptography technology. So now anything that's using the default IPsec profile is going to have the extra little goodie of PFS using Diffie-Hellman group 20 as part of it. To verify that, let's do a show crypto IPsec profile default just to make sure that the changes we made actually took, which is a really good practice. And sure enough, now we have the PFS that's enabled using Diffie-Hellman group 20, still using the default transform set. And because we did modify or customize the default transform set, we're going to be using the transform that was specified in that customized transform set. Our last step is to go ahead and create a tunnel interface. Now we could use a virtual tunnel interface to create virtual access interfaces, or we could use the good old tunnel interface straight up. Let's do that. So we'll create tunnel interface number 5. We'll say tunnel mode IPsec IPv4. We'll use the IPN numbered option that we have previously. We'll specify the tunnel source as E00 and the tunnel destination as R2's IP address that's reachable. And I'm also going to include this tunnel interface in OSPF in area 0. And then we'll apply our cryptography policy by doing tunnel protection IPsec profile default. Now to make all this work, we need a compatible policy for IKE version 2 and for IPsec over on R2. So because this is virtually identical except for the IP addresses are going to be changed to reflect R2 peering over to R1, we'll take this one a teeny bit faster. So let's go into configuration mode and we'll modify the IKE v2 proposal, the default one, and let's specify for encryption, data integrity, and Diffie-Hellman the exact same that we specified on R1. So everything regarding this IKE v2 proposal is identical to what we did on R1. However, what we could have done is just have at least one of each category. For example, one encryption, one integrity, one Diffie-Hellman group. As long as we have one that matches between the two, we're good to go. Of course, we want to verify that, so we'll do a show crypto IKE v2 proposal default just to make sure that what we put in is what's currently there as the default IKE v2 proposal. And that looks great. Now we do have a default IKE v2 policy, and we don't really need to change that because the default IKE v2 policy is pointing towards the default IKE v2 proposal. So right here, proposal default refers to this guy right here. So we don't have to modify the IKE v2 policy. We didn't modify it on R1, and we're not going to modify it here. Next, let's create our key ring right here on R2. We'll call it our keys. We'll set up a peer as R1. We'll specify his address. For identity, we're going to use the address of 15001 to identify that peer. And the keys we're going to use are Cisco 123. And in our example, we're going to use the same pre-shared key on both sides. Next, we're going to create our IKE version 2 profile. And I'm going to name this default as I did over on R1 as well. And a little reminder comes up, okay, we need to specify the authentication method for local and remote, and we need a match statement to go ahead and know who we're going to do that authentication with. So I'm going to say match identity remote address 15001. I'm also going to specify here on R2 that our local identity is 25002. And we could use various things for identity. We could use address, FQDN, email address, and so forth. So in our previous videos, we used FQDN. In this one, we're going to use IP address. Because R1 is emotionally and technically prepared to authenticate with us via pre-shared keys, that's what we're going to specify here as well. So we'll specify local and remote authentication. We're going to use pre-shared keys for both. For those keys, we're going to go ahead and use the local keyring called our-keys. And let's also set the lifetime. Now, lifetime is one of those few elements that doesn't have to match exactly because the two peers can go ahead and negotiate the shortest of the two lifetimes. But everything else, like encryption, data integrity, aka hashing, Diffie-Hellman group, the authentication methods, those items have to match. Now, on R1, we're using the default IPsec profile. However, That's calling on the default IPsec transform set, which we modified over on R1. So we're going to want to modify that here on R2 as well with the syntax crypto IPsec transform-set default, and then we'll use the same transform or transforms that we used over on R1. And again, we have the warning message saying, hey, you just changed the default transform set. Be aware this could have bigger implications if other sections of this router are also using that transform set. Now, because the default IPsec profile is using the default IPsec transform set, we don't have to modify that except for the fact that we said we want to use PFS with Diffie-Hellman group 20 over on R1. So we need that compatible policy right here on R2 as well with the syntax set PFS group 20. Next, let's create the tunnel interface here on R2 with interface tunnel 5, tunnel mode IPsec IPv4. We'll do IP unnumbered here as well. The loopback 0 is 2222 on R2. The tunnel source is going to be E00, which is the 25002 interface. Tunnel destination is the reachable IP address of R1 at 15001. And I'm also going to include this interface as part of OSPF. Now, I've got a question for you. What is the last thing that we need to do here to actually enable this crypto policy on R2? And if you're saying, ooh, Keith, I know, we need to apply that IPsec profile to this interface. If that's what you're saying, you are absolutely right. So to do that, we're going to use the syntax tunnel protection IPsec profile and the name of our IPsec profile. In this case, the name is default, indicating the default IPsec profile. And that is a very positive sign. The tunnel came up and the OSPF neighborship also came up, which implies that IKE version 2, that tunnel came up, as well as the IPsec tunnels. They also came up. To verify that, we can do a show crypto IKE v2 SA, and that will show us the security associations for IKE version 2. And this looks great. We are in a status of ready. There's the lifetime for our tunnel, and we've currently been up for 12 seconds. We're using AES 256, hashing of 512, Diffie-Hellman group 20, and pre-shared keys for the authentication. And if we want to see more detail about that IKE v2 SA, we could just throw on the tail end of that the keyword detail, and it'll give us more details on that SA. Now, one of the items that's specified here is dead peer detection, and it's configured for 0 seconds, which means it's not configured. So although it's an integrated feature that's part of IKE version 2, it's not enabled by default. So if we did want to enable it, it's pretty easy to do. We'll simply go into global configuration mode and say crypto IKE v2 DPD, which stands for dead peer detection, and how often we want to do it. 60 represents 60 seconds. If we're not able to see or hear back from a neighbor, we're going to go ahead and do retries at 2 seconds until we time out that neighbor. The option on demand, what that says is that if there's IPsec traffic going back and forth and you've seen that neighbor within 60 seconds, there's no need to send an extra IKE keep alive. So on demand says if it's quiet for 60 seconds and you don't know if the neighbor's there because you haven't seen his traffic, let's go ahead and send the keep alive in that event just to verify that the tunnel is still working. Now that will apply to future tunnels. If we do a show crypto engine connections active, we should have our IKE v2 as well as 2 unidirectional IPsec tunnels, which looks great. Now this isn't a very nice trick, but what we're going to do is we're going to go ahead and wipe out the security associations that are in place with a clear crypto IKE v2 SA. So we're going to clear it off. Why? Because I want to see it come back with negotiated dead peer detection with the other side. And the OSPF neighborship and the tunnel coming up are both very, very good signs that they've reestablished their security associations. If we use the show crypto IKE v2 SA detail again, same command we had previously regarding the details for IKE v2, we'll notice that this time that dead peer detection is configured for 60 seconds with a 2-second retry. And if we wanted that feature on both sides, we need to enable dead peer detection on R1 as well. To see our OSPF neighbor, we do a show IP OSPF neighbor, just to validate that we have a good neighborship over with R1, which we do. If we want to see the OSPF learned routes, we can do a show IP route OSPF, and we have one route that we've learned, that's the 10.1.1 subnet we've learned from R1, and it should be reachable. So let's go ahead and do a ping. Let's do a ping to 10.1.1.1. We'll source it from our 10.2.2 interface IP address, and let's do a repeat of, I don't know, what do you think? Let's do 1,000 pings across this IPsec tunnel. And with those pings done, let's do a show crypto engine connections active, and it should reflect the encapsulation and encryption of those 1,000 pings and any other OSPF traffic and so forth, as well as the replies back from all those pings. So here's our outbound security association for IPsec, and here's our inbound one. And of course, here's our IKE version 2 tunnel. I have had a great time in this video with you, and I would strongly encourage you to practice what we've done together in this video. Now, to assist with that, I've got these syntax for everything we've configured on R1 and R2 for the implementation and verification of IPsec with FlexVPN, along with all the customization that we've done to the defaults. Now, a little word of caution. You very likely will not want to change the FlexVPN smart defaults because you can have lots of different stuff going on that's using those. And if you make one change to a default, it has the potential to wreak havoc on another existing tunnel that thinks that default is something else. Now, the cool thing is this. Regardless of whether we're working with the default IKE version 2 proposal, or the default IPsec transform set, or the default IPsec profile, the syntax for working with those profiles, whether you're creating a completely separate one or whether you're working with the default, the syntax for the creation of those objects is the same. So this file is located in the Nugget Lab files associated with this course for your reference. Again, I've had a great time. I'm so glad you joined me. I hope this has been informative for you, and I'd like to thank you for viewing.